Hello, fellow students. Today we will talk about the reservoir performances. If you remember in the previous lecture, we said this lecture is for the petroleum engineers, the reservoir, especially those who are working in the reservoir and production department. Okay, so today we will discuss the well performance. As I said before, when we talk about the well performance, we have two main factors. In fact, we have it can be subdivided into the inflow performance and the outflow performance. So the performance of a well is governed by the behavior of two basic factors: the capacity of a reservoir to pass fluid against the downhole conditions, that means the inflow performance, and the ability of the produced fluid to flow through the well conduit to the surface, which is called the vertical or the outflow performance. So when we talk about the well performance, we have two things: the inflow performance and the outflow performance. Okay, the two factors are closely linked because the final condition of the inflow performance is the starting point of the vertical flow performance. It goes with that saying, because when the fluid leaves the reservoir, it flows through the wellbore, through the production conduit, and once it reaches there, that is the end of the inflow. From there starts the outflow. So the two factors are linked, they're closely linked. Okay, now let's talk about the well inflow performance. Okay, the well inflow performance is characterized by several factors such as the productivity and index, the straight line IPR, and the Vogel's IPR, the skin effects. Okay, you have to know that the when you start producing the well, okay, the reservoir is first of all at a constant rate. I mean, the production is constant, and at a certain level it start changing, it start moving. You will see it later. We will illustrate it on a graph. Okay, at that moment we talk about the Vogel's IPR, which is the inflow performance relation. Okay, the skin factors is about the flow, how the flow is in the reservoir. Okay, we will get to it and explain each term, each item deeply. Okay, in the inflow performance, you will learn about the Darcy law, including the skin factor. In the Darcy law, the liquid flow in laminar flow through a permeable medium is described by the Darcy law with the skin factor S, which includes the effect of the actual formation damage. So S here is the formation damage. This is the Darcy equation, where Q is the flow rate. Okay, the flow rate, that means barrel per minute or meter cube per second. Anyway, that is the flow rate. Okay, which is the value, the constant you see, multiplied by the permeability, and the pay zone. H is the height of the pay zone multiplied by the difference between the average pressure of the reservoir and the pressure at the wellbore, all divided by the product of the viscosity multiplied by the formation volume factor, the logarithmic value of the radius of the reservoir and the radius of the well minus 0.75 plus S. S is the skin factor, which is the reservoir or the formation damage factor. Okay, this value is always given. Okay, so you have to memorize, or you have to master this Darcy law, because you're gonna use it a lot. Most of the time, people make it in the Excel sheet. Okay, they have an Excel sheet where they just enter all the value and get the answer of the flow rate. Okay, this is the well performance equation. Okay, in case that we don't talk about the formation damage, then you can easily see that we did not include S here, which is the formation damage factor. Okay. The Darcy law, without including the factor liquid flow in a laminar flow through a permeable medium, is described by Darcy law without the screen factor S. Okay. If the medium of the flow is permeable, okay, then there's no S, which is the skin factor, which is the formation damage factor. In this Darcy law equation, as I said, cure is the inflow rate, which is standard barrel per day, and K is the reservoir permeability. H is the height of the pay zone, which is measured in feet. P is the average reservoir pressure, the P bar, as I said. The PWF is the well flowing pressure at the sun face. Okay, that means in the well bore, the pressure in the well bore. Mu naught is the viscosity of the fluid in centipoise. B naught is the formation volume factor, which is reservoir barrel of a standard barrel. Okay. RE is the drainage radius of the reservoir, and RW is the well bore radius. S is the skin factor due to permeability change. These equations apply for steady state. Okay, that means at a constant reservoir pressure. Okay, so if the reservoir pressure is changing, then the Darcy equation does not apply anymore. Please keep in mind that the Darcy equation is applied in the steady state. Okay, in a steady state. Okay, good. Let's move on. The productivity index concept. Let's explain deeply what is the meaning of the productivity index. Okay, the relationship between the well inflow rate and the pressure drawdown has often been expressed in the form of the productivity index. So the productivity index is simply the relation between the well inflow rate and the pressure drawdown. As we said that in a naturally flowing reservoir, our driving force is the pressure drawdown. Okay, so this pressure, to express the relationship between this pressure drawdown and the inflow rate, we have termed it the productivity index. And I would like to the well inflow performance indicators, the productivity index concept, which we are still talking about here. This is a common indicator of liquid reservoir behavior, is the productivity index, or the productivity index. As we call it, we most of the time we will write PI, which stands for productivity index, or refer to the productivity index as J in the Society of Petroleum Engineer nomenclature. In the nomenclature of the Society of the Petroleum Engineers, sometimes we write J, which stands for the productivity index, and J is the production rate divided by the drawdown. Okay, so cure, as we said, is the production rate. So for you to have the productivity index, you just divide the cure from the Darcy equation over the pressure drawdown. Okay, then you have the following equation, which is cure naught. That means the production rate over the pressure drawdown, and you have the value of J. Okay. Now, the inflow equation for oil flow can then be written as follow. That means the inflow rate is equal to the productivity index J multiplied by the pressure drawdown. Okay, here you have the inflow performance relationship as a straight line. As I told you, when you start producing from the well, first of all, you produce at a constant rate. Reason why the drawdown is constant. Okay, you can see here that the slope here is the drawdown. The line is declining at a constant slope. Okay, In this graph, you can see that on the x-axis we have cure, that means the production rate, and on the y-axis we have the pressure. Okay, we have the pressure. You already know that the reservoir pressure is higher than the the pressure in the well. That means the bottom hole pressure. Reason why, you can see on this graph that the average pressure of the reservoir, the value of the average pressure of the reservoir is higher than the value of the pressure in the well, okay, at the bottom hole. Okay, then you simply have the values of the pressure drawdown through the line, and when you extend the line at the zero reservoir pressure, then you have the maximum flow rate. Okay, the maximum flow rate is when the reservoir in pressure is zero. Okay, and this is valid for a single phase liquid flow. For a single phase liquid flow, the maximum reservoir flow rate happens when the bottom hole pressure is at zero. Sorry, I said reservoir pressure. I was talking about, it is my mistake, I'm talking about the bottom hole pressure. If the bottom hole pressure is zero, then the drawdown is maximum and the flow rate is also maximum. Okay, uh here from this graph, you will have all the time to see all the mathematical relations. It is obvious that J, which is the productivity index, as we said, it is Qion. No, that means the flow rate over the pressure drawdown. That means the value on the x-axis divided by the value on the y-axis. If you have the alpha, then tan alpha is simply equal to Q max over delta B, which is the, as I said, the change on the x-axis divided by the change on the y-axis. Okay, then this is on the graphical solution of the productivity index. When you graph it on a graph paper, okay, you simply have this, and the slope is -1 over j. Why is it -1 over j? Because the flow rate, as I said, the productivity index is the flow rate divided by the the pressure drawdown. And you can see here that the slope of this line is delta y over delta x. Okay, and I think it is the reverse. Okay, what I mean, it is the reverse of the productivity index. The reason why we have minus is because the line is declining. Okay, good. Let's continue. The factors affecting the inflow performance. We will see it in the next lecture. Good. Thank you very much. Feel free to ask all your questions in the comment sections.